Hello everyone. Welcome to this course on combinatorics. Our first lecture will be on one of the simplest techniques which is very often used in combinatorics. This is the method of pigeonhole or the pigeonhole principle. Now it may be the simplest in terms of the principle, the statement, and easy to understand. But that doesn't mean that it is by far the simplest to use. In fact, we will see several examples where you need to come up with some ingenious ways of thinking so that we can we can put the question into the correct framework where we can apply the pigeonhole principle. Okay, so what is this principle? This is something that all of us know by heart. By experience, and we might have already used it many times. So this says the following: suppose you have, let us say, let's say k plus 1 pigeons. A flock of pigeons comes, and then there are k plus 1 of them for some k, integer, positive integer k. And then these guys sit into, let's say, k pigeonholes, or k cages. Now, if k plus 1 pigeons sit into k cages, then we can say that at least one of the cages must contain 2 or more pigeons inside, right? This is something one can easily see, because if every cage had at most one pigeon, there are k cages, so there is at most k into 1, which is at most k pigeons inside, right? So therefore we have a proof for the same thing, right? So we can say it in terms of balls and bins, that you have k plus 1 balls and k boxes for bins. So here are the k bins, let's say, right? And into this k bins, suppose we are going to deposit k balls, right? Now, what I want to prove is that at least one of them must have 2 or more balls. So if I want to avoid that, then I will try to put only, right, at most one in each. But now I don't have a choice. I have to select one more here. If I have 6 balls, and I need to put at least 2 in one of them, right? So therefore this is easy to see, and this is precisely what the pigeonhole principle is. Okay, so the proof was that if each box has less than or equal to 1 ball inside, then at most k into something less than or equal to 1, right? At most k into 1 equal to k balls can be there. So that is the proof, right? Now, this supposedly and very simple looking principle, how do we use it? Can such simple statements have some real applications in mathematics? In fact, we are going to see many very nice applications of this in today's lecture. Yes, we start with a very simple example. Suppose you have 8 integers, and you are asked to show that out of these 8 integers that are given to you, there are 2 among them whose difference is divisible by 7. Okay, no matter which integers, right, are given to you, you have to show that two among them are such that their difference is a multiple of 7. Now, how do you prove something like this, right? So now, if you want to use pigeonhole principle, the two things I need to figure out are what are the pigeons and what are the pigeonholes, right? Once you know what are the pigeons and what are the pigeonholes, we can very easily apply the principle, right? Because you know that there is some pigeonhole with this many, and then use it to solve whatever we want. But the question is that what are the boxes and balls, right? So how will you come up with answer to this, right? What are the boxes and what are the balls? And that is where the difficulty is. Okay, in applying pigeonhole principle, always the difficulty is to figure out what are the boxes and what are the balls. Now, in this case, how will you proceed to solve this? Yeah, so let me state something very general in the start of this course. That combinatorics is a topic where you need lots of practice. You need to do several exercises to be able to solve questions, when you are asked for exams, for example, or like in later times. Because unlike every other area in mathematics, there is less there is less of a structural or general approach, but rather more of uh, more of a situation where you get some idea to click and then you can use it. You can use that idea to basically convert it into an already solved form or something like that. But or apply some general principle that you already know. But to be able to convert into that form where you can apply this, you need to come up with some way, and this usually is very different for each of the problems depending on the flavor, and that is what makes combinatorics one of the most difficult topics to work with. Now, the only solution to this is to solve as many questions as you can. So when we finish the lecture, we will have some questions for you. That definitely you should try to solve. But apart from that, you also look at the book. The books that we suggest have many exercises, and go through the exercises and try to solve as many as you can. This might be a little bit time consuming, but there is no other way. Okay, so yeah, so this is my advice. Now, another advice I want to say is that whenever a problem is presented to you for a mathematics course, in fact, in any course, this is something that you should do. But in general, here, in particular here, I want to say that once you hear the problem clearly, before the solution is discussed, you please pause and try to think about this. Okay? This is something this is an advantage of an online course where you can basically pause the video and then you can try to solve it on your own, because on the class you have very limited time. The teacher can give maybe a few minutes to think, but if he gives a lot of time for you to think, then of course he cannot finish the topics, right? So therefore he is much more restricted there. But on the other hand, for a lecture like this, where you have the option to stop the video and think about it, you should try to spend some time thinking, and then once you once you think about it, you may not be able to solve it, that is okay. Once you think, several ways, and then you see the solution, that will definitely help you in understanding the applications tremendously. Okay, so with that, let us continue. So how do we go about solving this question, right? So first thing that you observe here is that you need to show that something is a multiple of 7, right? So basically what you are talking about is divisibility, right? So divisibility by 7. Now when you talk about divisibility, what comes to mind is that if something is divisible, then the remainder is 0, right? So then you get an idea that, okay, we have to show the remainder is 0. No, we want to show that remainder is 0 for, right, what? The difference of two numbers. So when is the difference of two numbers have remainder 0? Well, if they have the same remainder when divided by the number, then the difference will have, that remainder will be gone, and then the difference will be multiple of the number that we are talking about, right? The difference will be 0 for the remainder. So remainder will be 0, and then we get a multiple. And that is what we are going to use here. Okay. So we are given 8 integers, and we have to show that difference is a multiple of 7 for some pair of them. So what we are going to do is that we take our integers and divide all of them by 7, one by one. So I take the first number, let's say A1, then A2, A3, etc., A8, right? Each of them I divide by 7. Then I get the remainders R1, R2, R3, etc., R8. Now, when you divide a number by 7, what are the possible remainders? Right? The remainder can be either 0, can be 1, 2, 3, 4, 5, or 6. These are the only possible remainders when you divide by 7. Now, we have 8 numbers which you got as the remainders, and each of the remainder now can be put into one of the boxes labeled 0 to 6, right? Because they are the remainders when divided by 7, so therefore it will be one of these numbers. So I'm going to put these 8 numbers into these boxes. So like an R1 goes here, R2 goes here, something like that, right? Now if I'm going to put it like this, then what do we know? Since there are 8 numbers, there will be some box in which 2 numbers will come, right? 2 of the remainders will be there. So that means that they must be the same, because I'm going to put a remainder into a box only if it is that number, particular number, 5. If it is 5, it is 5, right? The remainder is 5. So you take the corresponding numbers, let us say AI and AJ, for which the remainder is the same. So AI minus AJ has remainder 0 when divided by 7. That is why it is divisible by 7, right? Is a multiple of 7. So that's all there is, right? So once you figure out what are the pigeons and what are pigeonholes, that is it. There is nothing else. Yes, this is the first example. Now let us look at another example. Okay. So here the following question is given, that you are given a set with 11 elements. Now out of this set, you are going to make 4 element subsets. Okay? So you take any 4 of them, you get a subset. You take any some other 4, then you take another subset. So you pick 4 element subsets and take any 10 of them, whatever you like, right? So pick any 4 any 10 of the 4 element subsets of the 11 element set. Then 2 of these 10 sets that we are talking about must share at least 2 elements. Okay. So how do you show this? Okay, again, if you like, please pause the video and think about it. Now, okay, so here is the solution. So we are talking about two of these elements are going to have 2 or more elements in common. So if I want to show there are 2 elements in common, I can say that these subsets have, if you look at the 2 element subsets, they have an intersection. That is also good enough, right? If I show that these 2 sets have a non-empty intersection, right? And the subsets, 2 element subsets have non-empty intersection. That is also fine. So to do this, what I take is that I take each of the 10 4 element subsets, each of the 10 4 sets, and find and write down or consider the 2 element subsets above. Okay. Now, if you take a 4 element sets, how many 2 element subsets you can find? Okay, this is a question that you need to figure out. We will see the general method later, but most probably you are already familiar with it. One can easily show that there will be 6 of them. Okay? 6 of them are there, right? This is 6 each. So each 4 element set has 6 2 element subsets. Now there are 10 sets, so there are how many possible subsets? There are 60. So this gives 60 possible 2 element subsets. Now if any 2 of them are the same, that means that those 2 sets had intersection of size at least 2, right? So we want to show that this is the case, right? There will be 2 with this property, 2 will be the same. Now how do you show this? Well, we started with an 11 element subset, right? S is an 11 element set. Now you look at all possible 2 element subsets of this. So S has 55 2 element subsets. Now why? That is something that you need to figure out. Okay. Whenever I write why, that is the part that I have not given you proof, that you have to prove it yourself. You have to think about it and do it. Okay. So 55 2 element subsets are there. Now once you know that there are only 55 possible 2 element subsets, we can make pigeonholes, right? We make the 55 labeled boxes now with each of these 2 element subsets. Now we know that out of the 60 guys, each of them must be one of these 2. I mean one of the 55, because there is no other possibility. They all come from the set S, right? All the elements come from the set S. So I'm going to put the 60 guys into the 55 boxes. So 60 is more than 55. So therefore, one box must have at least 2 inside. And that says that these two element subsets are the same. And therefore, they must have come from 2 of these 2 different 4 element subsets that we are looking at out of the 10. So that is it. So we have proof that this is indeed the case. Okay, so here is the proof I have written here. Consider the two element subsets of each of the four element set. We show that some of the two sets must be the same. And for this, we look at the two element subsets of S as the pigeonholes. There are 55 of them. Again, think about it. Why? And each four element subset has 6 two element subsets. And again, why? And therefore, 10 into 6, which is 60 in total. By pigeonhole principle, 2 must be the same. And that's the proof. Okay. Now, the same pigeonhole principle we can write in a slightly more usable form, which I will say as follows. Suppose we have, instead of k plus 1 balls, let's say n into k plus 1. Now these are put into k boxes. So we have n into k plus 1 balls. We are going to put it into k different boxes. Then one of the boxes must have greater than or equal to n plus 1 balls inside. The same argument that we did earlier works, right? So here instead of 1 into k plus 1, and then instead of 1 plus 1, 2, we have n plus 1. Okay, because we know that if each box had at most n, then we have n into k, that is at most nk balls inside, right? So that is the proof. Now we want to use it to prove a very, very, very simple but very, very important result. Look at this example, right? It may look like nothing, but it is the start of a very big area in combinatorics, one of the most famous areas in combinatorics called Ramsey theory. And all this can be started from this particular question that we are discussing. But let us look at what is it for the time being. Okay, so any group of 6 or more people contains either 3 mutual acquaintances or 3 mutual strangers. So any group of 6 or more people. Okay, so you go to a bus stop, let's say, and you find 5 people sitting there, and with you there are 6 of them, or maybe there are 6 of them or 7 of them already. You join. There are many of them, many of you, and now the claim is that there will be at least 3 guys who have met each other, or at least 3 guys who have never met each other. Okay, so acquaintance means that like kind of friend, but if I meet you, but not really a friend or anything, then it's an acquaintance. But in short we will call it by friends. So there are 3 mutual friends or 3 mutual strangers, and we want to prove this using Pigeonhole principle. So how do you do this? Okay. Now, of course, we can use set theory to do this, but let us introduce a new concept just for proving this. Okay, this is a concept of graphs. What is a graph? A graph is a set. So you have a base set called a set of vertices, which we are going to denote as points or dots on the plane now, right? So here we have these dots, which are called the vertices of the graph. And then you have 2 element subsets, right? This forms a relation, a binary relation among the elements of V. Okay, so among the vertices, you have a relation which is called the edge relation. So whenever 2 vertices are in a relation, then I will say there is an edge, and I represent the edge by a line segment joining the corresponding vertices. And this is for the time being, this is a graph for us. Okay, so we have vertices and 2 element subsets, and now the advantage is that now this graph can represent many things. Okay, you can it can vertices can represent people, or it can represent terminals in a communication network, or or components in an electronic circuit, or many things like this. And then in the edges can be like, for example, the channels of communication, or you can say that like whenever I am, we are friends, then I put a line between them. There's a relation. Now we can even go further. We can say that I can represent different relations, like knowing and not knowing can be a relation. Now for knowing relation, I will put let's say blue edge, and not knowing relation, I put a red edge, right? Something like that. So now I can have colored edges, right? So if two guys know each other, then I put a red edge, or whatever, a blue edge between them, and if they don't know each other, I put a red edge between them. So these are called edge coloring. It's called edge coloring. So you have a graph and then color the edges, and the color can represent properties, right, or relations. Now there are many types of graphs. We will not go into details at this time. We might look more of this in later part of the course. But for the time being, if every possible two element subsets are present for a vertex set, then this is called a complete graph. Okay, so here is a complete graph on three vertices. There are three possible edges there. All edges are present, so it's a complete graph. So with this in mind, we are going to design or model our problem in terms of graph question. So what was our question? Any group of 6 or more people contains either 3 mutual friends or 3 mutual strangers. Now if you show that suppose there is 100 people maybe, right? But if you show that out of this 100, if you take any 6, even within that 6 you have 3 friends or 3 strangers, then the entire group also have 3 friends or 3 strangers, right? So we don't really need to look at the larger numbers. We can just work with 6. So that is one advantage, right? So we are going to represent now a graph with 6 vertices, where each vertex represents a person, and you have all possible edges, and the edges are going to represent if two guys are going to be friend or not. Okay, so if there is a blue edge, then I say those two guys are friends. If A and B are friends, then there is a edge connecting A and B with blue color. Okay, so I take the 6 different people. Okay, now if I suppose I pick up a particular person, right, this guy, I can talk about him being friend with the other people, right? For example, like let's say these two guys are friends, let's say, right? Either they are friends or they are not friends. So we assume that one of them is the case. So let us say that they are friends. Now I take this guy and this guy. Maybe they are not friends. Then they are going to be strangers, right? So I'm going to put a red edge between them. Similarly, we can talk about this particular first guy being friends with the remaining 3 guys also, right? Now, by our pigeonhole principle, the second version that we looked at, if n into k plus 1 balls are put into k boxes, some box must have greater than or equal to n plus 1 balls inside. Okay. Now, here we have 5 possible edges, right, going out of this guy. So if I select this guy, there is one edge, 2 edge, 3 edge, 4 edge, and 5 edges. 5 edges are going out. Now out of these 5 possible edges, we are going to color all of them with 2 different colors, right? Just 2 colors, either blue or red. If they are friends, blue edge. They are not friends, red edge. Now applying the earlier principle that we talked about, we know that since there are only two boxes and we are going to put 5 inside, at least one of them must contain 3 or more inside, right? So which means that for some 3 the color is the same, right? At least, right? So maybe they are the friendship or not, whatever, doesn't matter. Both are identical, right? Symmetric cases. They are either friends or not friends, right? So the 3 of them must be of the same color. Let's say that 3 of them are non-friends. I mean, the friends, okay? And then 2 are maybe all of them are friends. That's okay, but we just want at least 3. So now we know that at least 3 have the same, right? These 3 give the same relation with this. Now, what we know? So we have applied Pigeonhole principle. Okay, let us see, right? Now the question is that what can you say about these two guys, this person and this person? If they are friends, then I already have first. Okay, let us put some names just to be easy. So this is A, this is B, and this is C, and this is D, right? Now B, C, and D are all friends with A, right? Now B and C are friends. Then what does it say? It says that there is a blue triangle which says that all the 3 are mutual friends, which is what we wanted to prove, right, to begin with. So if there is a blue edge, then I am already done. So therefore I can assume that is a red edge. Now similarly, if C and D there is a blue edge, then also I am done because I get a blue triangle. So this must be red. Now between B and D, if it is blue, again I get a blue triangle, so it must be red. But then I get a red triangle between B, C and D. So if I don't have a blue triangle, I have a red triangle, right? Or maybe, this didn't happen. Maybe instead, this was blue. But then I have a blue triangle. So blue triangle means that there is 3 mutual friends. Red triangle means that there are 3 mutual strangers. So one of them must be always there. So this is what this result says, right? If you have any 6 or more people, there will be either 3 mutual friends or 3 mutual strangers. Now this says something very fundamental. Okay, we'll discuss a little more about this later. But it says that this is something very much like the Pigeonhole principle, that if you are talking about very large numbers, okay, 6 is not very large, but compared to 3, yes, it is. Yeah, if you're talking about very large numbers, then no matter how chaotic you try to make it, there will be still some order. Okay, that is what this really boils down to. Okay, so what we are saying is that no matter how you are going to color with 2 colors for the time being, right, or some fixed number of colors, we will see later, you can still find very structured subgraphs inside, smaller size but still with a lot of structure and properties that we are looking for.